Now, we were talking about API 577, so we'll start with the second video of API 577. We are going to start with section 4. Now, section 4 of API 577 talks about various kinds of welding processes. Now, we already know when we have seen ASME section 9 that there are a lot of welding processes. There can be oxy-fuel welding, there can be arc welding. Arc welding also have multiple types. You can have SMAW, GMAW, GTAW, flux core arc welding, plasma arc welding, various types of welding processes in arc welding itself. Then you can have solid state welding processes such as friction welding. You can have fusion welding, you can have electron beam welding, laser beam welding. There are various kinds of welding processes. But an API authorized inspector need not need to know all of these things. Okay, we generally concentrate on most kinds of welding operations that are used in fabrication or repair or alteration, which are generally going to be arc welding processes, because arc welding processes are much suited for large scale operations. The simplest is going to be SMAW, so we'll talk about those. So the inspector should understand the basic arc welding processes most frequently used in fabrication and repair of refinery and chemical process equipment. These processes include shielded metal arc welding, that is SMAW, gas tungsten arc welding, that is GTAW, glass metal arc welding, that is GMAW, flux core arc welding, which is like GMAW but slightly bit different because it also have flux associated there. Then you can have submerged arc welding, you can have stud arc welding and plasma arc welding, electron gas welding. All of these are most common welding processes that are generally going to be used in repair and alteration or fabrication of equipment. But out of these, SMAW, GMAW, GMAW, GTAW, and in some extent, submerged arc welding are generally used. But again, there are possibility of you using more than a welding process that are listed here. Okay. The descriptions of less frequently used welding processes are available in bibliography. Each process has its advantages and limitations depending on the application and can be prone to specific types of discontinuities. So depending on what kind of welding processes that you're doing, some discontinuities can be associated with those as well. So let's imagine I'm talking about shielded metal arc welding. So we are generally using a flux there. So flux can now get converted into slag and you can get slag inclusion. There is a possibility there. But in GMAW, where there is no flux involved, you cannot get slag inclusion there because it is not possible with that manufacturing process. Okay, so something like that. So the first is going to be shielded metal arc welding. So SMAW is most widely used arc welding processes. The SMAW creates an arc between a covered electrode and a weld pool. So you have an electrode that is covered with a flux, and you use the arc that is created between the electrode and the workpiece. The shielding is provided by the decomposition of the electrode coating without the application of pressure and with the filler metal from the electrode. Either an alternating current or a direct current may be employed, depending on the required mechanical properties, welding power supply and the specific electrode selected. So you can use an AC current, you can use a DC current, both are possible. But generally a constant current power supply is preferred. Okay, it's a constant current process. So if your electrode is closer to the object, your voltage is lower. If your electrode is far away from the object, your voltage increases because it's a constant current process. So it's something like this, where you have an electrode. So this electrode is something like this. So you have an electrode that is made up of a metal and you have an electrode coating. This coating is a flux which acts as a protective layer between the weldment and the surrounding areas. You have this electrode holder, you have this power supply. One terminal is connected to the workpiece and the other terminal is connected to the holder and the electrode. Something like this. So your electrode melts, the metal melts and the coating also melts. It creates a surrounding area where your weldment is protected from the environmental conditions. A layer of slag deposits on the weldment which can be removed by cleaning the pass after it is done. So electrode covering, depending on the type of electrode that is being used, the covering performs one or more of the following functions. So you can have multiple coatings. You can have cellulose coating, you can have ferrous oxide coating, you can have potassium coating. Other types of coatings are available. The terminology is given in ASME section 9, which tells you what kind of coating characteristics you have. It depends on the number that is written on the electrode, but it provides gas to shield the arc and prevent the atmospheric contamination of the molten filler metal, provides scavengers, deoxidizers, fluxing agents to cleanse the weld and prevent the excessive grain growth in the weld metal, establishes electrical characteristics of the electrode, stabilizes the welding arc, and influences the operability of various welding positions. Provides a slag blanket to protect the molten weld metal from the atmosphere and enhances the mechanical properties, bead shape, and surface cleanliness of the weld metal. Provides the means of adding the alloying elements to produce the appropriate weld metal chemistry and mechanical properties and to increase deposition efficiencies. So either of these, one or more than one of the following things can your electrode coating do. So advantages, the following are most commonly accepted advantages of an SMAW process. It is the most easiest process. Almost every welder knows how to do SMAW process. It's a manual process. It's sometimes also known as manual metal arc welding process. So it is relatively simple, inexpensive, and the portable, because you just need a power source, a holder, and an electrode, and it can be very portable there. The process can be used in areas of limited access. The process is less sensitive to wind and draft conditions. The process is suitable for most commonly used metals and alloys. The level of training and experience required is lower than the other welding processes. Next is limitations. The limitation are going to be the deposition rate is going to be slower than other processes, because first of all the deposition rate is slower. Next is when your electrode ends, you need to install a new electrode and you would have to do welding again. That means one electrode is generally going to be good for 3 minutes. So if you have a longer amount of weld that you need to fill, then it is going to be impractical. Secondly, after every process you might need to clean your weldment because there would be slag there. Okay, the slag must be removed from the every deposited weld parts at the starts and stops before depositing the adjacent bead or onto a previously deposited bead. If you don't do this, then you might get slag inclusion. The next kind of process that we are going to talk about is going to be GTAW, sometimes known as TIG welding. So GTAW is an arc welding process that generates an arc between a non-consumable tungsten electrode and a weld bolt. So here your electrode does not melt. Electrode is made up of tungsten, which is not going to melt. It is just going to create the arc between the electrode and the workpiece, and you can have an additional filler metal that you can use to melt it and fill on the metal. This GTAW can be done with or without filler metal also. So if you're doing with filler metal, extra filler metal is needed. If you do it without filler metal, then you just melt the two pieces and you join them together. Okay, this is a commonly and somewhat correctly referred to as TIG welding or heli arc welding, and is used with a shielding gas. So here there is no slag to protect your weldment from the environmental conditions, so you will have to apply an additional shielding gas to it. This shielding gas is going to be any kind of an inert gas or inert gas combination. You can have helium, argon, sometimes CO2s can also be used. Without the application of pressure, GTAW can be done with or without filler metal. The constant current power supply can be used either AC or DC depending on the largely on the metal to be welded. The direct current is typically performed with the electrode negative polarity. So if you are placing the electrode on the negative side, then it is electrode negative. The DCN refers to offers the advantage of deeper penetration and faster welding speeds. So this is the representation of TIG welding or GTAW welding. So you have this cylinder which is going to provide you the shielding gas. This shielding gas is going to be either any kind of a shielding gas, it can be any kind of inert gas such as argon or helium or CO2 also, so, or a mixture of those. You have this electrode holder. This electrode holder has a tungsten electrode. This inert gas or the shielding gas is going to pass through this tube and it is going to pass through the nozzle which is located at the tip of the electrode. So it is going to create an envelope so that your weldment can be protected from the environmental conditions. This is done with filler metal. So here is your tungsten electrode which does not melt. This is a filler wire that we are using. So this filler wire will be used and this filler wire would be melted and deposited on the weldment, and this would be your base metal. And this area around the electrode is going to facilitate your shielding gas to pass through the weldment and create a protective environment. Advantages: GTAW is one of the best kind of welding process if you want a very clean weld. So it is one of the best processes because the operator have higher degree of control over the welding arc. So it produces a high purity, generally free from defects, requires little post weld cleaning because there is no slack to clean, allows for an excellent control of root pass weldment. So in most cases the root pass is done by TIG welding or tungsten arc welding, and the additional filler passes can be done by some other processes which are going to be much faster. The main problem with GTAW is it is very slow. Okay, it can be done with or without filler metal dependent on the application. The process is relatively defect and contaminant free for the root pass. The limitations: lower deposition rates, so it is very slow, low tolerance for contaminants on the filler or base metal, difficulty in shielding the weld zone, especially in the drafty environment. So the GTAW is not going to be preferred for outdoor welds. It is generally going to be preferred for indoor welds where you can control the environment. If you are doing outdoors and if you have wind and draft conditions, it is not going to be as effective because your shielding gas would be blown away. Next is MIG welding or GMAW welding. GMAW arc welding processes produces an arc between a continuously fed filler metal. So in this case, you have a filler metal that is in the form of a wire. Okay, so you have an electrode holder, and this wire comes out depending on what is the rate that you have set in. So once you press the button, the wire comes out. This wire will melt and deposit on the weldment. Okay. GMAW can be automated, semi-automated, or sometimes manual also. It employs a constant voltage power supply and uses either a short-circuiting, globular spray, or transfer modes. So the transfer that is going to happen from the electrode to the workpiece can happen in 4 ways. You can have short-circuiting method, you can have globular method, you can have spray or pulse spray method of metal transfer. The transfer mode is going to be determined by various factors. The most influential are the magnitude and type of welding current, electrode diameter, electrode composition, electrode extension, or the contact tube to work distance, and the shielding gas. So in this case, this is going to be your wire reel. So this wire is going to come through this welding gun and it is going to deposit here. The same tube is also going to provide the shielding gas. So the shielding gas is also going to be provided. So it is going to create an environment around here where your weldment is going to be protected from the environmental conditions and your filler metal is going to get filled. This wire reel will have a huge chunk of wire there. This means this welding you don't need to stop. You can do continuously until you run out of wire. So this is going to be having a very good deposition rates. It is going to be much faster, and cleaning is also not required cleaning is also not that important in this case because you don't have any slag deposited here. Okay, something like this. So different types of metal transfer. You have short circuiting method. The short circuiting method is not generally used. It can be used for thinner metals, but if you use it for thicker metals, then you can have a problem of lack of fusion. Okay, so GMAWS, that is short circuiting, encompasses the lowest range of both welding current and electrode diameter associated with GMAW process. This process produces a fast freezing weld pool that is generally suited for joining thin sections, out of position welding, or root passes. Due to fast freezing nature of this process, there is a high potential for lack of sidewall and interpass fusion, the welding thick wall equipment, and nozzle attachment. The shielding gas transfer mode is typically 75% argon and 25% CO2. So we are not going to use short circuiting method very much, provided if it's a very thin metal. The modified short circuiting GMAW mode, designated as GMAW MSC, has several proprietary derivatives from the short circuiting transfer mode that uses a waveform to reduce some problems associated with short circuiting, mainly spatter, turbulent flow, and weld pool. The GMAW MSC mode minimizes disadvantages of GMAWS, that is short circuiting, while maintaining the comparable weld metal deposition rates and achieving X-ray quality welds. The welding process has the capability to complete open root more rapidly than GTAW with low heat input and resulting in lack of fusion. The lower heat input results in smaller heat affected zone as well as reduced distortion and lesser chance of burn through because the current is very low. The process appears to be more tolerant of inexperienced welders because GMW MSC is tolerant to gaps and capable of automatically maintaining the arc optimum wire speed and tip to workpiece distance while allowing the use of large diameter GMW consumables. Mostly we are going to use a globular or a transfer mode. So the advantages of this globular transfer mode is it is relatively low cost when carbon dioxide is used for shielding gas, along with higher deposition rates. The maximum deposition rates for globular arc mode is 250 inches per minute. The globular arc transfer mode is often considered to be least desirable SMAW process due to tendency to produce high heat and poor weld surface and spatter as well as cold lap. It can be used in some cases where you have extremely high thicknesses. Spray transfer mode, again most widely used. The spray transfer mode results in highly directed stream of discrete drops that are accelerated by the arc forces. Since these drops are smaller than the arc length, short circuits do not occur and the amount of spatter generated is negligible. The maximum deposition rates are going to be 150 inches per minute, and the transfer mode is typically 98% argon and 2% oxygen depending upon the wire diameter and amperage. The shielding gas may have composition of 80% argon and 20% oxygen. Pulse transfer mode. Pulse GMAW was developed to overcome the thickness and welding positions of globular, spray and short circuiting modes. This transfer mode provides a low background constant and sustain arc without providing the low energy to produce the drops at the tip of the wire. Superimposed pulsating current with amplitude greater than the transition current necessary for spray transfer. The maximum deposition rate is going to be 200 inches per minute. So what are the advantages? So at this level you just need to understand what are these welding processes, and just by understanding what are the welding processes you can easily determine that what are some advantages and limitations for that, and you can also understand what are some common discontinuities associated with that process. So in GMAW obviously we cannot get slag inclusion, we cannot get tungsten inclusion, but in TIG welding we can get tungsten inclusion but not slag inclusion, something like that. So advantages: it is the only consumable electrode process that is used to weld most commonly commercial ferrous and non-ferrous metals and alloys. Its deposition rate is significantly higher than obtained with SMAW and GTAW. Minimum post-weld cleaning is required due to absence of slag. Limitation: the welding equipment is more complex, more costly and less portable than for SMAW. Obviously this can also be done indoors. Okay, outdoors you would not prefer it because if there is a wind and draft condition it will not be as suitable. The welding arc must be protected from air drafts and that can disperse shielding gas. When using SMAW short circuiting process, the weld is more susceptible to having a lack of fusion types of discontinuities. As a result, the ultrasonic examination is generally employed as the inspection method because the probability of detecting lack of fusion is rather lower in radiographic testing. Flux core arc welding. Flux core arc welding can be seen as a derivative of GMAW process. In GMAW process you have a filler metal that is a solid wire. In F-core welding you have a filler metal that is essentially a tube which has a core filled with flux. Okay, so you have a tubular wire, inside that you have a flux, and then you can process your welding operation. This can be done with and without shielding gas. Okay, so you can use a shielding gas to get additional protection, but it can also be done with without shielding gas because you have a slag coverage there. So flux core arc welding process that produces arc between a continuously fed tubular electrode and the weld pool. The process consists of a shielding gas evolved from the flux contained with the tubular electrode itself or without the additional shielding that is provided by the external supplied gas, and without the application of pressure. The recommended power source is going to be DC, constant voltage type, the similar to power sources used for GMAW. It is essentially GMAW, just the filler wire is very different. Filler wire is a tubular shaped wire with a flux inside it, so flux core. Something like this, the same process, just the filler wire that you have, it's a tubular shaped wire and it has a flux at the core. Advantages: the metallurgical benefits that can be derived from allowing elements contained within the flux. The slag that supports and shapes the weld bead allows for slower cooling rate, higher deposition and productivity rate compared to SMAW and GTAW. Shielding produced at the surface of the weldment make it more tolerant for stronger air currents than GMAW. Limitations. The following limitations are associated with flux core arc welding. The equipment is more complex, more costly, and less portable than SMAW. Self-shielding flux core arc welding generates large volume of weld fumes and requires suitable exhaust equipment. The slag must be removed between the passes. So if you have a slag, if you don't remove the slag, it can do slag inclusion later on. Backing material is required for root pass, and self-shielded flux core arc welding is typically not recommended for pressure containing welds. Then you have submerged arc welding. So in submerged arc welding, essentially your entire part is filled with flux. So you have a flux hopper that actively deposits flux on the surface, and you have an electrode that moves behind that flux hopper and produces a weldment. So in this case, the weld is happening beneath the solid flux cover, so you will not be able to see that welding torch. You would not be able to see that UV light that you generally get from a welding operation. The welding would be done beneath the solid flux cover. That means an operator cannot see where the welding is happening. This is generally going to be an automated process, but it is going to have a very high deposition rates. The submerged arc welding is generally going to be used for sections that are generally 2 inches, 1.5 inches or 2 inches or thicker. Okay. So this process can be used without pressure and with filler metal from the electrode itself, and sometimes from a supplemental source. The submerged arc welding can be applied in 3 different modes, that is automatic, semi-automatic and machine mode. It can either use a constant voltage supply or constant current supply. So it's something like this. This is your flux hopper, so it actively deposits the flux on the weldment, and this is your electrode that melts the electrode and deposits the weld. This is happening beneath the solid flux cover, so you'll not be able to see the visible arc coming out of it. Advantages is going to be it has very high deposition rates and produces a repeatable high quality welds for large weldments and repetitive short welds. Limitation, the power supply capable of providing high amperage at 100 duty cycle is recommended. Weld is not visible during the welding process. The equipment is more costly and extensive and less portable. The process is generally limited to shop application and flat positions, because if you do vertical weld, your slag would fall off. If you do overhead, your slag would fall off. Okay, so only flat position and horizontal positions can be done with this. Then you have stud arc welding. Stud arc welding is not generally used, but it can be used where you want to attach stud to the metal plate. This is more widely used in marine operations for ship repairs. The stud arc welding process generates an arc between a metal stud and the similar part of the workpiece. The stud gun holds the tip of the stud against the workpiece, and the surfaces of the part properly heated, then they are brought into contact with the application of pressure. So let's imagine this is a stud, this is a workpiece. So you'll have this workpiece and the stud with some of a gap between them. You'll produce an arc and then you would stick it, okay, with some amount of pressure. The stud arc welding is a specialized process predominantly used for welding insulation, refractory support pins to the tank, pressure vessel and heater casings. Advantages: high productivity rate compared to manual welding the studs to a base metal. It is considered to be an all-position process. Limitations: the process is primarily suitable for carbon and low alloy steels. The process is very specialized for fewer application. Then you have plasma arc welding. Not widely used, but it is a modification on GTAW process. Okay, so plasma arc welding is a variation of GTAW process, except that the tungsten electrode is positioned within the body of the torch. This process is rarely used in fabrication and repair of the pressure equipment. There are 2 types of plasma arc welding process, specifically the transfer process and non-transfer process. So transfer process, the plasma or ionized gas is forced through a fine bore copper nozzle, which constricts the arc and exits the orifice at a high velocity at the speed of sound, and the temperature can be achieved as excess of 11,100 degrees Celsius. Non-transfer types of process, the plasma spray process is solely used for deposition of surface coating. It is not used for making strength welds. So you can see advantages and limitations. Not widely used. Again, with electro gas welding, you can just read it, but not widely used. So this was all for section 4. In section 4 we have seen the commonly used welding processes, what are some functions of it, what are some advantages and limitations of it. Now in the next video we'll go for section 5, which is going to be welding materials. What are some base metals that are used, what are some filler metals that are used, what are some ancillaries that are used during the welding process. We'll talk about those. Okay, this was all for this video. Let's meet in the next video with the section 5.